Good morning, everyone. Very happy to be here with Romain to give you a little training on geospatial data analytics and mobile operator data, and specifically call detailed records. So before we get started, I'm going to share my screen. Can you confirm that you can see the slides, please?
Coming up? Yes, it's up now, Sophie.
Yeah?
Yes, it's up
Okay,
now.
great. Thank you. Right, so before we were meant to introduce each other, but we're just going to skip that because thank you, Anu. You gave a very thorough presentation. So before we go into the core of the training, I'm just going to give you a very brief overview of who we are. So Romain and I are working for the Flowminder Foundation, and we are a nonprofit based in Stockholm, Sweden, Switzerland, and the United Kingdom. And we aim to use novel data type and specifically mobile operator data and geospatial data to support decision making in low and middle income countries. So everything we do is with the aim to improve the well-being of populations in these countries, with a specific focus at the moment on Africa and Haiti. So we first started in 2010 when our founder, Dr. Benson, got the idea of basically estimating the movement of population using anonymized mobile operator data to see how people got displaced after the 2010 earthquake. And he used similar methodology later on that year to work on the cholera outbreak in the country. So that work shaped the Flowminder Foundation as we are today. And our aim is to work on novel data type and providing analysis on population and mobility to support a wide range of applications such as disaster, public health, or official statistics. So, and one of the things we do is also capacity strengthening. So this is why Romain and I are here today, is to empower and enable people in various countries to actually do what we do or develop their own geospatial data or mobile operator data analysis for the common good. So we have an hour and a half together today. There is a lot of content. So we're going to go very quickly on the theory, and then Romain's going to go through some practical activities to actually go into the value of the data. So the first part is on GIS and geospatial data analytics. I'm not sure whether the previous speaker gave you any theory around GIS and geospatial data. So I'm going to take a couple of minutes just to be safe, and then we'll go into the activities. So geographical information system, or GIS, is basically a computer-based tool for mapping and analyzing things that happen on the Earth. So we're using database combined with visual map interface to map and analyze objects and events on Earth. So that can be buildings or that can be people, because much data that is involved in the management of the environment or people has a geographical element. So it has a position on Earth. And we use that information. We organize such data by its location on the map to analyze and make applications and use cases for decision making. There's different type of questions that GIS can help answer. So GIS, we're looking at it as a decision making, like a decision support tool. So some of the applications that you can use GIS for could be like identification. So finding the name of a city, finding out where a point of interest are. So whether it's a public health facilities or a school or vaccination center. What is the shortest walking distance between two given points? What are the patterns in building footprints, which should suggest the type of building? Where are the newborns located in a country? Where have there been new homes been built in the past 10 years? So there's thousands of questions that GIS can help answer. And there are different models and scenarios that you can apply it for. So why it matters, why is GIS actually helpful? So here we're showing you two maps. So Flowminder, as Anu has explained before, was working for the Grid 3 partnership. We were co-founder and implementing partners. And in the work we did in Grid 3, we actually did a lot of work in Nigeria around geospatial data analysis. And here we've got two examples of maps. So one hand-drawn map that used to be produced before Grid 3 got involved, and then an improved digital map. So here we're really looking at the accuracy of the data and how we can actually make better decisions. So GIS has two data models, raster and vector. So raster data model is actually modeling what we call continuous features. So it's data that can be measured anywhere and form a continuous surface. So we're looking at things like elevation or slope or temperature, as opposed to vector, which actually map discrete features and is describe individual features and where they are located. So you've got different type of discrete features that we're looking at. Point, polyline, and polygon. So a point is basically when we're meant to locate where the object is. There is a shape and a size of the object that we put on the map, but it does not represent the actual shape or size of the object or the people you are putting on the map. The line basically covers a distance, not an area. So it's looking at the position and the length of the object you're mapping, but it doesn't give you an indication of the surface. And finally, polygon is basically an enclosed area with defined boundaries marking. So here you're looking at the extent of an area covered. And you can use different features depending on what you're trying to analyze and the message you're trying to convey. So if you're looking, for example, at a point, you can use it to map point of interest. So where is a hospital located or where is the epicenter of an earthquake? A polyline can be a river on a road, and a polygon can be, for example, a forest. So what's the extent of a forest in a country? And you can use a combination of these features depending on the street. So for example, a car park, if you just want to say where it's located, you can use what we call a point. And then if you want to show the extent and the size of that car park, you can use the polygon feature. And the value of GIS is you can make detailed and easily updatable data visualization. So the data you're working from that database can be produced and turned into maps to actually visualize and interpret the data you're looking at. So here we've got a map of, well, a zoomed in map of Kaduna State in Nigeria. And this is part of our work on optimizing the service site placement. So there is a combination of vector and raster data. So the green bits are gridded population estimates from WorldPop, and the purple points are the location of existing site with a buffer, which determine a zone around a feature. And there is the zoomed in version, so you can see the combination of the different data types. That's the very, very quick theory. Hopefully that made sense. I'm going to pass it on to Romain to go more into the practical activities and how you actually apply GIS for decision making. So I'll stop sharing. Romain, you can take over.
Yeah, thank you, Sophie. I'll say thanks again for the very thorough presentation. And so I'll pick it up again from here. Let me see, sharing screen. Can you see my screen, everyone?
Yeah, we can.
Okay, perfect. So before we start, I'll just say one thing in particular that, concerning a little bit this session. It's I've had issues with my personal work computer, which is currently out of service. So I'm using a different computer currently. So if I'm taking a little bit of time to find the right places, etc., bear with me. I only have one screen and I'm using a different system currently. One thing I'll say, so we were quite ambitious, I think, in the sense that we prepared a lot of content. I'm not sure if we will have time to cover everything thoroughly. But having said that, keep in mind that all the material will be shared with you. All the links will be shared with you, and this presentation will also. So it's very likely that we'll have to go over quickly over some of the details. I'll try to keep the time. But if something is going too quick, or if you miss something, you'll be able to go back to this yourself, and particularly to run all the codes I'm going to show you right now. So geospatial data. So we are going to have a first activity here, presenting some basic, perhaps I shouldn't say basic, a simple at least analysis to gain some understanding of the data sets. how we can use it for decision making, and mostly, I think, to get you inspired on ways you can use this in your own work if you do not already do. So this will be the activity I will be starting very soon. Just a few words on that before we start. What's the purpose of this exercise? So essentially here, as an example, we want to assess the coverage of health facilities. And in this sense, we want to assess their coverage, to observe the access for women that might need it for maternal health care. So we'll be using a couple of geospatial data sets. I'll provide you with the links to download those yourself. If you want to run this with other types of data, I mean, I will share with you the link to the World Data Platform. As it stands, the code will be shared with already provided data sets. So if you were to set this on your own machine, everything would be provided to be able to run this exercise. So here is the important link. So I'll go there right now. If you can't catch it now, that's fine. Again, since we have a short amount of time, I'd rather have you following with me, following along the exercise. And when you have more time and, you know, when you can find time yourself, you know, to go through this and go through the different steps, you just need to go on this link, download everything, and you'll be able to get going. Okay? So let me switch to this particular page. So if you were to follow this link, you would land somewhere here, which will contain all the material you need, and also all the information needed to start this work. All of this is essentially Python code running on JupyterLab. So that's the thing I'll be showing off to you right now. I'm not sure if all of you are using Python or JupyterLab, so there is a couple of information on how to download the repository you have here. So this is a GitHub page. So how to download the repository, how to create the environment you need in Python, meaning when you're installing Python, you will need specific geospatial libraries to be able to run this code. So all of this is set up there for you. And once you have all the material, well, you just run it on your side and start exploring, essentially. So what this would look like in practice, if I'm bringing up a terminal. So if you're following the instruction, you will have some information about installing the Anaconda software. It makes your job way easier to have everything set up. And part of the software will provide you with this Anaconda PowerShell. That's useful if you're using a Windows machine. If you were on Mac, you should perhaps already be comfortable, perhaps not, but at least know that you have already available a shell, a command shell on your machine to run the exact same instructions. But if what I'm saying now is confusing you, just go on the Anaconda PowerShell and run the following commands. All right.
Hello, Romain.
Yeah.
In 1 minute, can you please zoom out your screen? It seems extremely small.
Oh yeah, I can do that. Can everybody see the terminal at least? And I'll make the rest bigger in a second. Can everything see what's happening here?
What you're typing is, I mean, what you have there is obvious, but still looking at.
I mean, currently it's just a terminal to run the commands and start the practical.
It's good now. It's better now. Yes.
Okay, perfect. So important things to notice. Currently, I'm located in this particular folder. I'm in my base environment. And as I said before, I've created an environment for you to be able to run those codes. So that's the thing I'll run just now. I'll activate this GeoPython environment. All right. So if you cannot see clearly or understand clearly, again, all of this information is provided on the GitHub page. So essentially, I'm just activating the environment, and then I will start JupyterLab. So you will see a bunch of comments showing up. And that's the place I'll stay to run the code. All right. Let me put this full screen. You will land on the folder that contains all the information you need. And among them is this first practical that I'll start right now. Is this readable or is this visible? Is this big enough for all of you to follow? If I can just have one confirmation that this is...
And they're asking if you can zoom in a bit.
Zoom in slightly more? Okay.
Yeah.
Something like that?
You can zoom in a bit. If you can have it a bit more. Yes, I think it's better now.
Are we good?
Yes, we are.
Okay, perfect. So first exercise. So we want to assess the health facilities coverage in Kaduna State in particular. So that's a place we've chosen randomly for the sake of this exercise. You could run something similar in any kind of places you can imagine. So our problem is essentially that we will have a data set which contains the health facilities in the region. Let me just reduce something. Okay. So we'll have the health facilities in the region, and we want to know which one might be overstretched, meaning potentially we have too high a number of people that might depend on this health facility, and in particular for women that are childbearing age. So we know they might need this facility for delivery, and we want to make sure that all of them have are not over a certain threshold of persons depending on them. That's essentially our problem. We want to identify this target number of people per health facility. So this exercise is purely geospatial, but run entirely in Python. So to do this, we will go through a few steps. So first of all, of course, we need to load our data. We'll subset this data to particular points of interest. I'll show you more on this in a minute. Do some basic aggregation and use some geospatial techniques to help us answer our question. And we'll try to identify these particular connections between the dataset to set targets, so a certain number of people per health facility. So I'm running this live. The same exact thing would happen on your machine if you were to run this code. So as usual, with anything Python or programming, you would first load the libraries you need. And in there, you can find a couple of different libraries. There are general purpose ones, which are more data science oriented or about loading your data like OS to find the path. We have a couple of geospatial libraries. In particular, to deal with rasters, to deal with vectors, and some other nice things to do some maps. And a couple of visualization libraries to be able to make some plots and visualization. Okay. So first step, we're going to load all of our data. I have a raster with the population data. I have my healthcare facilities. And two other things I will need is the state boundaries and the wards in the area. Okay. So I've run this is loaded. And just know that this data is provided on the GitHub, but if you want to explore more, I've provided you with links that will guide you to the data portal. And here you can find a whole wealth of data sets available. So in different countries, or if you're interested more particularly in data available in Nigeria, you have this second link here that will guide you to all the data sets available. for different other types of information. Okay, so our healthcare right there, which has been loaded previously, we are just gonna first explore the data, and we want to see what's in there. So I'll just run this, and essentially what I'm doing here is just choosing specific columns to display. So I can see that I have some geographical information, latitude and longitude, some category information, names of those health centers, categories of ownership, where they're located, etc., and some geometry information, because here we are dealing with a data object that is called a GeoPanda, which is essentially a data set, as you can see now, a table with categories and rows, but that also contain geographical information. So this geometry column you can see here. And this is very useful for our purposes because we have everything in one place and we can easily map this. You will see this in a second. And for the purpose of this exercise, we are only interested in public health centers. We want to see which public health centers are available for the population at large. So we can do a quick selection here. So again, I won't have time to explain all of the details due to the time, but you can easily go back to this in your own time and look at all the instructions to understand what's going on. But here I'm caring only about the public healthcares. So that's the ones I'll be selecting. And you can easily see that I switched from more than 2,000 places to something like 800. So if I look at the ownership, now everything is public. That's my initial healthcare dataset. Okay, so we have the data we need. Now we perhaps want to understand a little bit what's going on, and we want to see it mapped. GeoPanda provides you this very nice function called Explore. All of the stuff here is nothing very complicated. These are just a bunch of parameters to tell the method how to plot my data. But the thing I want to do is first load the words. So I'll do this now. And then load the public healthcare I've just created previously by selecting the public-owned healthcare centers. So I'm creating two variables from them. And now I can display the information. So this is something quite useful to have in the Python environment because you can quickly create a map, provide some information that is of interest to you in an interactive environment. So as you can see, I can move around, I can zoom in particular places, I can have information on the words, so where am I located? And so if I'm zooming in on Kaduna, I can also have a look at the different health center I have selected with some category here to know what they are, essentially. So all of this, starting from the GeoPandas, I can create this interactive environment and start exploring my data a little bit. Okay, so we have the districts, we have the healthcare centers, and the last thing we need now is information on the population. So we want to know how many people are located in which places. So I will be loading now my raster data. And for this purpose, I'm using this library called Rasterio. Here I'm gonna do a simpler plot, simply to show you the raster dataset and to ensure that everything is working. So you can see the title here is Women aged 15 to 49 in Kaduna State. And that's because the raster we provide with the code already only contains this information. So say if you were to start with a general population data set that provides you with information about the categories of population, then you would have to go through the selection process yourself and create a raster that only contains the information you need. But for the sake of this exercise, we are providing you with the data already prepared. And here you can see the population counts across the region for this specific category of people. Okay, so we are all set. We have our spatial data and everything seems to be in order. So our initial question is finding out the health facility coverage across space of each of these particular health centers. And there are different ways you can go about it. What you want is divide the space and allocate the space to each health center. But this space should be meaningful in the sense that this should be for the people located in the space around the health center. You would assume that those are the people that would go there. And you could imagine using a road network, for example, how easily accessible the health center is by road. Or perhaps you could go and interview people. It could be very likely that even though a community is located very close to a particular hospital, maybe they wouldn't go there because they prefer going to another one that is further away. So there would be different strategies that will give you different methods and precision. For the sake of this exercise, otherwise we'll use a purely geospatial methodology, which will be dividing the space using Voronoi polygons. So if you've never seen this before, what this algorithm does, is essentially dividing the space, as you can see in this animation. And from each point, which would be our hospitals, propagate the space until you meet the propagation of another hospital. And what this tells you is that everything located, say, if we look at the purple here, any person located in this particular polygon is closest to this particular point. So this is a nice way to divide space, to allocate all the closest places to each hospital. Okay? So that's the method we'll be using right here, which can already give us a good indication of what's going on. So when you're dealing with geospatial data, always remember, and especially in a Python environment, which might not be as explicit about the projection of your data. Say if you're using ArcGIS, QGIS, you would usually see in the interface the type of projection you're using. Here I've just loaded spatial data, but if I'm not asking the spatial data, its particular projections, I would have no clue. And the thing is, if you want to do this work, you need to ensure that all your data is in the same coordinate system. So we can have a quick look here. Simply using the CRS keyword, we can have a sense of the coordinate reference system here. So we can see that we are using WGS84. That's a very common projection system. And that's a geographical system, meaning our information is given in latitude and longitude. Since we are dealing with areas, here we'll switch from this system to a projected system, which will deal with information in meters instead. So there are many different systems, coordinate reference systems that exist. In fact, I've put you the links there if you want to learn more about them. So that's the WGS84. That's one of the most commonly used. But the first thing we'll do is reproject our data, all of the data, so the hospitals, the state boundaries, Kaduna State, and all the wards to the same coordinate system, which is this one, which is essentially a projected system located in Nigeria. So I don't know if you can see so well, but here you will have the link if you want to know more about this one. What's important is that now we are switching opposition measurements in meters in a local coordinate system. All right, so here we simply use this function toCRS, and we'll switch from one system to the other. To ensure this worked, we can actually check. So if you remember previously, I was at WGS 84. I've reprojected. I'll have a quick look again at the hospitals. And now I get my information and I know that I'm in this Cartesian system with meters there. Okay. So one thing you can notice here, if you look at the geometry, those values are now in meter. Previously, I'm going a bit quickly, sorry about that, but here is the previous table. Here was lat long information. So very simply, I could switch from one system to the other. Okay, so now we have states, we have districts, and we have hospitals, all in the same reference system. So now we can attempt to create our Voronoi polygons. Here there is a couple of operations to be done. They are not of importance for this exercise, but essentially, if we want to run this particular algorithm to create the Voronoi polygons, which is a function available through this library called Shapely, we just need to select the right information to provide for this to run smoothly. So we only select the geometry information from the 3 datasets. That's essentially what I'm doing here. And in this environment, if I just call the variable, I can easily have a quick look at what's going on before running the algorithm. So polygon state properly represents my region. Point healthcare contains only the public healthcare facilities that I've selected before. And based on those points, I'm going to propagate the Voronoi and I'm going to limit them to the boundaries of my state. So let's run this algorithm. All right, this is already finished. And now I can have a look at the results. And this is how it looks like. If I plot it in a very naive manner, I can see that some polygons have been created here. So I'm going to extract everything. My Voronoi polygon, and reproject everything back to the original coordinate system. So my Voronoi, my healthcare, and my state boundaries. And we can have a look at the result instead using an interactive map. So it's a little bit more visual and understandable for our own sake. Okay, so now you can see that properly each of my hospitals is allocated this boundary that is the closest area to each of those places. So similarly as before, you can easily explore the data set, see what has happened, have a quick look at it, see if anything is, looks strange. But so far it looks like this worked. And now we have the possibility to allocate those spaces to each particular hospital. And now we can start looking at the population in those particular areas. So now the strategy is we have the hospitals, we have the area closest to each of those hospitals. Now we need to know how many people are living in each area, right? A function to do that is called zonal stats. And what this will do is use our population raster and calculate statistics on the data. The statistic that mostly interested here is the sum. We want to count the total number in each Voronoi polygon. Just know that you can produce a lot of different statistics here. So using the Voronoi and using my raster of population, I'll produce the sum of all the people in each of those places. Now comes the point where we'll have two types of data joins. So I'll provide a little bit of details on those. I'm not sure if you guys are already fluent in Python or not, so I'll try to still give some information on that. You might already know this, but it's still a good refresher. Data join. So in this case, the stats table, in fact, if I just show it to you right now. So stats table will contain the information I asked for each of my places. What I want to do is link it back to my Voronoi polygon, because this table exists separately, so to say. Again, if I show it, here I only have the results of my calculations, but they are not really allocated to each of the areas. So that's the first kind of data join I'm going to use. And it's named differently in different programming languages or systems. Here it's called join in my particular case. And what this will do is take this table with my statistics and join it back to the polygons. So before running this, Before running this, if I just have a look at the polygon so far, it's essentially just a collection of geometry. I want to attach this new information here to my table. So I'm going to do this join then with my stats data. Okay. So I run this is done. And for the sake of the exercise, we're going to rename the column to be a little bit more clear. So you could see that before my first stat was called mean, the other is sum. So we're just going to rename those to population mean and population sum. And now, from just having the geometry to each of these polygons, I also have my calculation attached. I know the average population in the area and the sum. So the average we are not really interested about here. I just put it as an addendum, but the sum is the one we are interested in. Now, second type of join that you can do, and this one is specific to geospatial data, is a spatial join. And here, instead of just connecting these two data sets together, what we're interested in is the spatial relationships between the data sets. Since the information now is attached to the Voronoi polygons, we also want to attach it back to our public health scares to know for each public health scare how many people are linked to it. We don't really have an easy way to do it doing a data join, because we don't really have common fields. Usually you would attach two data sets, and if they have the common fields, say an identifier or something, you can easily link them together. Here we do not have that. But instead, we know that each hospital is located inside a polygon. And that's the relationship we will use instead. So since each hospital is located in a Voronoi polygon, we use a special join, which will be looking at whether or not those two geospatial datasets intersect. So you can see here it's denoted as S-join for spatial join. And what I'm saying here is for the public healthcare, spatial join the Voronoi polygon. And since the healthcare is inside each individual polygon, they will be linked spatially. So here we are really looking at the spatial relationship. That's the important differentiation to remember. And that's the important thing to remember when you're dealing with spatial data. So let's link the healthcare with the Voronoi polygons by their position in the landscape. And have a quick look at the data to make sure everything has been properly attached. So I can still see my hospitals. And now I also have this value of population sum here on the side. Okay. We can do a final check. This one is more, say, data analysis related. Usually you do more checks than that. You want to ensure that everything has worked. But the quick thing we can look at is make sure that there is no row that is missing a value of mean or sum. And here it seems that all of our hospitals have been attached to value of population. Okay, so now everything is in place because we have the hospital and we have the approximate amount of people they cover. Now comes the part where we can start answering our question. So let's imagine our target is for each hospital to have a maximum of 4,000 women that are childbearing age. So I'll just set my target. And we can have a quick look. So I can plot a quick histogram of the situation, so a histogram of my population sum, to see a little bit the distribution that I currently have. So in this situation, I can see that I have most of my facilities below this target. And in fact, the data is quite skewed on the right side, meaning a few here, still a significant amount, but a few here that are above my target that are a little bit critical, and fewer, but which are extra critical, that cover actually a lot of people. So you could easily play around with this target. It's just a matter of changing the number, and everything is automatized, so everything will be produced for this new value. But let's stay with this for now. So we know some areas might be problematic. Now we need to identify them, right? And that's the final thing we'll do for this practical. So we want to identify the areas that are above target. And here it's a simple fact of selecting the values of population sum that are above the target I've selected here. So I'll do just that. And I'm doing this with the Voronoi because I want to display in red the areas. So it's a little bit more visible. And essentially with this simple instruction, our work is done. This last bit here, again, it's a very long piece of code, but most of what you see here is just parameter to display the data. I'm going to plot my Voronoi, the original one. I'm going to plot the outliers. That's the one I've selected, which are above my target of 4,000 women. And I'm going to plot the public health care. So let's run this bit. And now I get my final result. And I can actually locate all the areas that are potentially problematic. So then it's a matter of reusing this data for other purposes if you need to do a deeper analysis. Or if this is enough, you could easily export this as an HTML and have this interacted by potential end users. And all those areas in red are the areas where focus need to be given. So time is short, I'll leave it at that. But one final thing I would say, essentially a lot of this you could do in GIS software, right? And in fact, depending on what I need to do, I would sometimes use ArcGIS or QGIS. Now, the benefit of this is that everything is automatized, right? So it takes a little bit of more time to set up. But now, since everything is automatized, and say, I went through all of this work, but I realized at the end that I've made a mistake. And in fact, I should have selected other places. Perhaps I was not interested in the public facilities, or my target is wrong. Well, the only thing I will need to go back to do, perhaps I'll leave the facilities. That's an easy thing to fix also, but it will take a little bit more time to run. But let's say I've just mixed up my targets. I would just need to come back here, change the target. I would just restart. In fact, you could just run the code from here, but I'll just show you how to do that. So I'll just restart everything, run all the code again, and everything is put in place to give me my answer immediately. So I'll go back to the end. Now I have a new target. So now he's going through the process of loading the data, creating all the Voronoi, etc. again. Now I have a new target. This figure is automatically displayed. And I have my new critical areas. So you can save a lot of time and do a lot of exploration once everything is set up in this manner. Okay. So as said, I hope this made sense. All of the material, again, is available. Let me see, I will have to move this a little bit. Let me close these different tabs. Everything is available here in the GitHub, and you should be able to run all of this on your end, okay? All right. So moving on, this was the geospatial exercise. Now we'll go a little bit more into CDR data analytics. So CDR standing for Call Detail Records, in essence. Yes. So we've covered the geospatial data. Now we'll focus on the mobile operator data analytics. And that's essentially most of the work we do at Flowminder. So we use mobile phone data to study human mobility. So I'll provide you with a little bit of background here. Again, for the sake of time, I won't be able to go too deep into the details. But just know that with this presentation, a lot of links will be provided to you if you want to learn more about the things we do, the things you can do yourself on your own. So a very quick crash course on CDR data analytics. What would that be? So a CDR essentially is a metadata record of a telecommunication transaction. So every time someone uses their phone to call, send a text message, or even use internet data, this information is stored by an MNO, so meaning a mobile network operator, for billing purposes. They need to have this information to know how much you need to pay for the service you're asking when you're using your phone. As a minimum, so this can be very different depending on the mobile network operator, but as a minimum, such information will have an identifier for a subscriber, the timestamp, meaning when this transaction occurred, and a cell tower ID. So which cell tower relayed the communication. And the cell tower data, as you can imagine, is a special dataset that contains the position of the cell towers that form a mobile phone network. And here as a minimum, so we will have an identifier of the cell tower that should be the same as the one in the call detail records. So you can link these two data together. But since we are here dealing with a spatial dataset, call detail records are not a spatial dataset. This one is, and this one will contain the position of the cell towers in the landscape. And so how does all of this work? You have a situation where you have a user that will say, for example, make a call in location X. So that's the example you can see on the side here. Let's imagine our subscriber is this person in purple, and the cell tower is this green color here. Perhaps he'll have, a call there. This will be registered by this cell tower. So we know at this point, the user was somewhere in this location. Then he will move on, continue with his day, perhaps move somewhere there, have another transaction that will be relayed by this tower here. We know at this time of the day, this person was in this particular place, etc., etc. So that's the inferred movement. That's a very theoretical example. That's really to show how this works. But while this person is moving around and using his phone, those transactions are recorded by cell towers, and that gives us an indication of potential position of this person. And all of this information is recorded by the mobile network operator. And I'll just say the sake is not to profile or follow individual subscribers. This is really not the purpose. And in fact, this example is only showed for you to understand what's happening. But individual subscriber information is always protected at all times. This is personal private data. So we do not work with individual level information. But that's really to show you how this works. One thing of importance here is also to notice that this comes with a certain spatial resolution, right? We don't know the exact position of this person. We know the position of the cell tower that relayed the call. Hence the importance of, as you've seen in the previous example, here I've divided the landscape with volatile polygons. You can have other strategies to do that, but all of this would be the space closest to this tower. So we could imagine that the person was located somewhere in this area. So as I said, we do not deal with individual level data. What we do instead is aggregate this information. So in a typical day, you would have millions of transactions produced in one day. The entire population of a country subscribed, I should say, to a particular operator. So the subscriber base of the operator will be producing those events while using their phone during the day, creating millions of records. And what we do instead is aggregate the information to have a sense of human mobility. So again, here as an example, if you imagine 5 different traces, so those would be people moving during the day. Say if our question is how many people were located in this area covered by these particular cell towers in this particular day, those individual traces would be aggregated. And what we would actually see is that we had a certain number of subscribers at this time and in this location. And again, in fact, here I'm showing an example with 5 subscribers, but we would never produce aggregates for less than 15 people, again, to protect individual privacy. So this information would only be given to you in the form of aggregate. You would not see those trajectories, simply know how many people were at a certain time in a certain place for this particular question, and only if we have more than 15 subscribers. Okay. I'll go quickly over this because I'll show you more of this in a minute in the practical, but that's essentially what the call detail records look like. As I said, a CDR dataset for a day can have millions of events. So you can imagine that for a longer time period, say if you're looking at CDR data over a year, you can easily have billions of events in this situation. It depends on the size of the subscriber base, how often they use their phone, etc., etc. For our own sake, what matters is that each person will have an identifier, which is anonymized, meaning we do not know who is the person that produced the events, but we have a way to follow the same identifier in the dataset. So we don't know who they are, we just know this is the same person here if we look at the first few rows. You will have your tower identifier, the type of events, and the time there. So why bothering with all of this, and why be interested in all of this? Well, using this data, you can estimate population movement and changes in population density at a very large scale. So you can monitor variation in movement over time. You can have ideas of what happens before or after specific events. It's a data set that is generated in real time. In fact, every time you use your phone, this information is saved by the network operator. And as said, so contains a lot of data. So you would typically cover a large proportion of the population over a very large spatial scale. So entire country, but if you're interested in regions, you can, of course, narrow your focus. And we have a relatively high spatial and temporal resolution in those movements. So all of these reasons makes it quite valuable. Here are some examples of questions you can answer with CDR. So where are those people located over time? What are the patterns of movement in an area of interest? How many people are moving out or in and out at any particular point in time, or how many people have moved in or out? So here there's a slight differences. You can look at daily movements, pendularity, say you waking up, going to work and coming back home. Or you can be instead interested in longer time periods, movement, meaning where someone is living and whether or not they might relocate their home, etc., etc. So there are many types of questions you can answer with CDR data. I'll skip over this one because for purposes, it's not very important, but you have it available in the presentation. And the last important point, though, that I want to emphasize again is that all of this is done while ensuring privacy of individual users and transparency of our methods. One key point is that those insights should never permit the identification of individual subscribers in the work we do. And in fact, so we are compliant with GDPR, so the General Data Protection Regulation in Europe. And all of our methods are transparent and peer-reviewed. So those methods are open source, the algorithm, also, and we have also many publications in peer-reviewed academic journals. So this is very important. All right, so I'll go back to the activity. So this will be the second practical, same as the first one. All of the data will be available to you. And in this situation, what we're going to do is first, we're going to put ourselves in the shoes of someone that would be playing around with CDR data and perform a first mobility analysis. And here, again, the data is provided to you, but what I'm providing you with is a synthetic CDR data set. Because as I said before, CDR data is personal information, it's private, it would never be shared publicly as I'm going to do now. So this is a data set that is being produced by a model instead. It's replicating kind of realistic simulation of movements. Of course, it's not perfect. It's been produced for the sake of the exercise, but this is not real data. Again, real data would never be shared publicly. It would stay at the mobile network operator system. Similar with cell towers, because those can be critical. You perhaps can imagine that the position of cell towers can be a very important business information for a network operator, and is generally nationally sensitive. So in terms of security type of information for a country. So this is also a synthetic data set. And the usual world and region boundaries needed to see where we're in space and do our work. Okay. So again, provided here, the address is exactly the same. Same GitHub link, you would link here, you would end up here. Having done all of this process already, you would already have all the data on your own computer. And you would end up on this Jupyter Lab like I've done before, so I can close this one. And I will open instead the second practical, so CDR analytics. All right. So you have more information here. It's a little bit the things I've just explained, but again, critical part is the privacy of the data. Here we are playing with fake data to learn more about it. In reality, we do have to find indirect ways to use it. So classical thing in Python, first now we're gonna be loading our libraries. So again, data science tools and geospatial libraries. What I've done here is create a mapping function just to make the mapping of the different data sets a bit more straightforward, sorry. So it's a definition, so it's a new function that is now available to us to easily map different data sets. I'll let you have a look at this in your own time if you want to learn more how to do that. But important point, so we get started. What do we need? So we start with our CDR data. That's a subset of a CDR data. And let's imagine we don't know anything about it yet, so we are just going blind. So we'll be loading the call detail records, the CDR data. all of these phone transactions. Admin 1, here, which stands for the regions in Nigeria, and admin 2, which will be the wards or the districts. And finally, cell towers in the area. So let's load all of this. So all of this is located in this data folder here, coming with the code. And so we are going in blind. Let's have a first look at what's going on here by producing a first interactive map. So producing this, something I perhaps haven't shown before, but here on the top side, you can select actually the layers you want to display. So it's a little bit crowded. I'm going to remove the districts. We're going to focus on the region. And you can see I have my regions and my cell towers in the landscape here. So synthetic data set in a real case scenario, you'd probably have much more cell towers than there is currently, but that will do for exercise. And one thing we can observe is that the cell towers, of course, are not, how would you say? They are not regularly spaced in the landscape, right? You would have a higher concentration in places where you have more population to service them so they can use their mobile phone. So you can easily play around with this data set, have a look around. If I click on the different places, I can get the name of the regions. And hovering over each of these red dots, you can have the identifier of each individual cell towers. Okay, so we have a sense of how everything looks like. The data seems to be not problematic. I mean, we have the correct boundaries. We seem to only have cell towers in the country. So we'll move forward. One thing worth mentioning, so as I quickly talked about this before, but when you're dealing with GeoPandas, the default type of data created is called a geodata frame, which is this data attached to a geometry object to be able to handle geospatial data. So here I'm producing a fancy map, but you wouldn't have to do this. I'm doing this because it's more practical for my case, but it's very simple to produce also a very simple map. So again, looking at the CRS, I can see that my region are projected on this coordinate system. And if I want to do a very simple map, it's simply using the geospatial data and calling the plot function. That's pretty much it. So it's not as fancy, but you can already have a look at the districts here. So a good reminder here, you don't need to go all of the trouble, it's just more practical. So we are going in blind. So first thing we're going to do is have a quick look at the structure of each of our data sets. So we have the regions. So it seems we have the name of the regions and the geometry of each polygon. And if I'm looking at the info, that's a nice method to remember. When you're using this on the data frame, when you're looking at the information, you can get a summary of what's going on there. So I can see that I have 37 regions there with two fields, so name and geometry. Let's move on to the districts. So here I have 775 districts. Seems that I get a name and a geometry. The cell towers. So close to 1,000 cell towers, and each of them has a position and an identifier. And final thing, the call detail record data, so the synthetic data set. And here I have a little bit more information. This can vary quite a bit, depending on the data set you're working with. But as I said here, we at least have the minimum to be able to work with. So we have an identifier, and that's an individual identifier for each of the transaction. We have a call date. So when did the transaction occur? So you can see here, for example, something happened at 5:51 on the 1st of January, 2016. We have an anonymized identifier for the subscriber. That's the one that made the call. Same for the person that received the call. So we know this was a call from this person to this person. although we can't tell who it is, we have this identifier that's describing as one individual. And finally, this location ID, that's the identifier of the cell tower that received the call. So we will first do a little bit of exploration. So for convenience here, I'm essentially just creating a new column called day that instead of having the full call date, will only contain the day of when the transaction was occurring. So if you want to have a look at this, you can see now I have this new day column, which contains only the date of the day. And let me see. So we still have something like 15 minutes. So I'll probably run some of those examples. The rest, you have them available, so you can run them yourself. What's important here is when you're dealing with data like that, first step is, of course, data exploration. You want to have a sense of what's going on in your data set before attempting to do anything with it. So I'll answer a few of those questions, and then we'll move on to creating an actual mobility indicator. So how many cell towers are unique? Do we have duplicates in the dataset? I can use the number unique function to look at that. And it seems I have this number, so 993 unique cell towers in my dataset. Okay, so how many events here instead? And here you have 3 different ways to look at it. You can look at the count, but this can be tricky if you have potential duplicates. They might be counted twice. You can look at the number of unique events, and this will give you a more accurate representation of the data set. Or you can simply drop the duplicates, potential duplicates you have there, if you have some, before looking at the size of it. But looking at that, it seems we have around 150,000 events in our call detail records dataset. We don't really know which period it covers, so we can have a look at that. So what I do is look at the day column, pick the minimum, the maximum, subtract those two, and display this in a nice fashion. So I know that now my dataset goes from the 1st of January to the end of March, so roughly 2 months of data or 60 days. How many unique subscribers do we have? That's another interesting question. So we have 150,000 events, but if I look at the unique count of subscriber, we have close to 5,000 people in there. So 5,000 people that produced something around 150,000 call records. We can also have a first estimation of the number of events per subscriber per day. So I would simply take here my number of subscribers. So divide the total event counts by the total number of subscribers and divide it by my full-time period, which is 60 days. And I know that on average, I have half an event per subscriber per day. Something perhaps that you're not familiar with, so I'll just take a second to explain that. Group by function, this one is kind of a bread and butter function when you're doing data analysis. So here, we want to know the count of unique events per individual subscriber. So to do that, we're going to use this group by function. And the way this is used here, what I'm saying is, from my call detail records, group each individual MSI SDN, so that's the unique subscribers. And when grouping them, count the number of unique events, so that's the N unique here, that happen for each of those subscribers. So I'll just run this and show the result to you so it makes sense. So running this grouping by subscriber, now for each individual subscribers, I'm counting the number of unique events. So I have a sense of the number of events that each individual person has done. Group by is very useful for a number of different situations, and I'll be using it quite a bit in the other questions below. But since we have this information, we can also easily plot an histogram from it, and we can have a sense of the number of events here per subscriber in general. So slightly normally distributed, although we have a skew here on the side. So most people seem to be having, say, around, let's say, under 30 calls over the period. And we have a few here that extend and are very active users that are actually producing more events, so using their phone more than people in this area. So I'll pass over quickly on the different questions. Let me see if some of them are perhaps more important. You can run this on your own side. So all of this is about data exploration, understanding the data sets, and making sure we understand what's going on before attempting to produce mobility events. And I'll skip on that for the sake of time, so you can do this on your own after downloading the material. So there is a number of other questions we might ask ourselves, and the answers and how to get them are provided previously. Last one, we can do a group by, and here on the cell towers. And here instead, we group by the cell towers by region. And I'm able to do that because just previously, I'm linking the cell towers to my regions here using the spatial join strategy we've seen previously for the previous practical. So each cell tower is located in a particular region. So we attach that region information to the cell towers. So you can see that here, each ID of cell towers is linked to a region name. And based on that, we can count the number of cell towers in each of those. So we have a sense of their distribution in the landscape. Okay, so let's assume we've gone through all of this process. We have a sense of what's happening. We know how many people are in the data sets, how they use their phone usually, the number of events, etc., etc. Now we are ready to produce an indicator. The way this works, and again, that's the two types of joins I've explained before. The CDR data can be linked to the cell towers based on this common identifier they have. So each call data record will have the identifier of the cell tower, so you can essentially attach this information together. And administrative areas, such as regions or districts, can then be attached to cell towers by spatial join, by their location. And that's the way we combine all of these three data set together to have call detail records. By being attached to cell towers, we know the position of the cell tower. And by attaching them to an administrative area, we then know where the event occurred. Okay, so it's a step-by-step process by attaching all of this together. Here I'm calling it, to keep it simple, located CDR data, as you can see here. So that's the process of locating the data by joining it to these other data sets. We know the position of the cell tower, thus we know the position of the region. And if we know those two, we know where the event occurred. So I already have this information for the cell towers to the region. Those are my cell towers, and I know their position compared to regions. And I'll just then merge this back to my call detail records to have them located. I've stripped a little bit the call detail records to only keep the information that matters to us. But what we have here now is a day. So we know when this occurred. We know who did the event. Here you can see the correspondence between the event that was recorded in the call detail records and the ID of the cell towers. And since the cell towers was attached to the region, now I know when this call happened. Okay. So we have all of these. I'll just do a final cleanup so we only keep what matters. But now I know the position right here. I know the person and I know the time. So let's imagine now we're interested in looking at the total subscriber counts per day per region for this time period. So in other words, we want to have one value per day in region, which is the total number of persons that were active there on this particular day. I'll go quickly over this, but as usual, I've provided you with links to some of our knowledge center. So it's called FlowGeek. And this will give you more information about the different types of what we call aggregates that can be produced when asking these kind of questions using call detail records. But since my question is how many people per day and per region, that's what I'll use in my group by. So I'll group per day, I'll group per region, and for each of those, I want to count the unique count of subscribers. I'm doing this, then I'm only keeping results for regions that have more than 15 subscribers. And I'm finally displaying the results here. So here you can already see that for each day, for each region, I'm starting to see how many people were present in each of these particular places. I'll skip over that. I'll leave this to you. But that's a little bit of a difference between counting people over a whole region compared to looking at mobility. Essentially, since people move, the data might behave in ways you might not expect, but I'll leave this to you. But the thing we can do is a first naive plot of the aggregate. So that's what I would get. Here I can see my count of subscriber per region per day. You have all your list of regions here. And this first naive plot is a little bit difficult to read, right? You have all of these counts here located at the bottom. It seems there are two regions that have more people located in them. And it seems that something happened here for this particular place, some kind of event that produced this signal. We had around 100 people, say 150 people on average present there. Suddenly something happened. We are close to 500 and a drop afterward. So some kind of mobility happened. People moved there. By sorting those, I can see that this place is Lagos. I mean, I could have a look at the colors here, but it's a little bit difficult to read since we have so many regions. But on average, it seems that Lagos is the place where suddenly many people moved. So we're going to transform this to make this a little bit more readable. Yeah, so sorry about that. For the sake of time, I will have to go quickly over it. But the strategy is to create a baseline. So a normal period of mobility to compare the rest of the period to. Since we know something happened around, say, just having a quick look around the 11th or 12th of January, all of this will consider it as our normal period of mobility. So I'm selecting specifically this period to create my baseline. So that's the median number of people present in each region during this time period. Yeah. So calculating this, I'm selecting the time period of interest, so before the 11th of January, this one included. And I'm calculating a median from that. So I know, on average, I should have this many people in each region. I'm using this baseline to divide my daily values now. So instead of having just an absolute count of people, I will know the proportion of people in the region compared to what should normally be, what I call my baseline. In a standard situation, I should have that many people, and that's what I get for this particular day. So now I'm comparing to a normal period of mobility. Using this, I can do a final plot. So I'm just transforming my data slightly to have the information for each region, and I'm going to plot this again. So now everything is centered on 0 because everything is compared to this normal period of mobility. And now I can start to have a little bit more sense on what's going on. So I can still see this huge peak for Lagos. But if I was to quickly look at the data here, I could see that it seems there is some kind of drop here for most regions and an even bigger drop for a few regions here. Since we are dealing with daily data, it's very noisy. So I'll just instead plot this again by using a rolling mean. So I'm averaging the periods a little bit to smooth the behavior. And now I can see a little bit more clearly what's going on. So suddenly a huge increase in this particular region. I think a few here, 3, 4, maybe 4, 5 regions here with a big drop. And most regions a slight drop before coming back to normal. So I know something happened there. And that can be the start of my mobility investigation. With the same information, we can plot maps. Here I'm calling this map 18 because I'm focusing on the data of the 18th of January. And I'll plot the same proportion, but spatially. So looking at it, I can see, okay, on the 18th of January, I'm way above the normal for Lagos, it seems. And it seems these few regions located nearby have seen a drop during this period. And all of the other regions have also seen a drop, but a slightly smaller drop in comparison. So here is the start of your mobility questions. Naively, if I was to look at this, I would just imagine that perhaps on this particular day, there was a huge event happening in Lagos. And it seems many people located nearby traveled to this place during this week. People located further started traveling there also, but in fewer numbers compared to the normal. And a lot of people were located there during this period. So here is the example of a very simple first mobility analysis. Of course, you can do much more with CDR data, but I hope this gave you an idea of how these things work and how you can use them, or we can use them and work, and you can play around with the data set to observe patterns in there. So I'll leave it at that. Again, everything is available here. Sophie, if you're around, I don't know if you want to say some last few words.
Maybe it's worth, there's a question in the chat. Maybe you can answer that before we wrap up. And if there's any more questions, we can maybe stay around a couple more minutes to answer them in writing.
Yeah.
So Romain, there is a question around, someone's asking, if we were to obtain data for route optimization case study in logistics, which data should they look out for and where can they get such data? And then there's a specific question around the notebook, the Jupyter notebook, which we can answer in writing.
Yeah, okay. Route data, I guess I'll answer this quite generally because it depends on your situation. But if you would have road network data that contains, say, information on congestion, speeds, etc., you could run your own model, spatial model, to know how much time it would take to travel those roads. So say instead of using the Voronoi polygon as we've done for the hospitals, you could use your road network and propagate in there to know which hospitals people are likely to go depending on road condition. There are, I think, ways to do that in Python, in GIS, etc. Where to find such a data set, to be honest, I'm not totally sure. This will depend on your use case, to be honest. Generally, I know that OpenStreetMaps has some data set available, at least openly.
Yeah, we tend to look at grid 3. Sorry, Romain. We tend to look at grid 3 data. So we shared earlier the URL, which is data.grid3.org, which have a lot of things for Nigeria. Then OpenStreetMap is a go-to place. And sometime on HGX as well, you can find some open source data. But you Google and then it might not be they might not be all accurate or recent, but that would be the first places to go to.
Yeah. The second question, I'm not sure, is it about the notebook?
Yes, about interactive charts. But we can take it offline, that one. We can answer in writing. It's very specific.
Yeah.
Anu, I think
So
we're out of time, aren't we?
Yeah, so I was actually waiting for you to finish up, Sophie. It's nice connecting again, Sophie and Romain. Thank you for always doing justice to this very topic. We are very glad to always have you contribute to Bootcamp every year. Please confirm that you can hear me clearly. Can you hear me clearly?
It's not great, but
Okay.
it's
But can you
we
hear me
can
now?
manage.
Can you
Yes.
hear me clearly?
Yep.
So I
Yeah.
was saying thank you very much for always contributing and giving back to us. I mean most especially every time. We are very glad to have you. Thank you for your time, Romain. Thank you, Sophie. It's nice connecting with you again. So on behalf of everyone here, I want to say thank you for your time and thank you for impacting the community at large on this very important usage of call detail records or mobility data as it were. So we are glad to have you. So please can we appreciate Romain and Sophie? So thank you very much. So